Hello again, my name is William Pye, and in this video we are going to be revisiting the properties of connectives. While we have covered these properties before, we now aim to integrate these properties into proofs. The properties of the connectives have been discussed and demonstrated previously over the course of episodes 4 and 5. However, episodes 6 and 7 introduce the notions of argumentation and proof. So, what role do the aforementioned properties play in the development of a proof? Well, here, the properties of the connectives will be revisited and recontextualized, serving both as a review of the previous material and to streamline later proofs. Many properties of the connectives were stated as equivalences, so a useful relationship to establish is how a biconditional can be seen as an implication. Specifically, if you have that P is equivalent to Q, this implies that P implies Q. As an argument, this statement can be written in the following way. That is, the premise will be P is equivalent to Q, therefore the conclusion is P implies Q. This argument can be shown to be valid using a string of equivalences. Specifically, we're going to be using very heavily the restatement of the implication and the biconditional. So here we go. I have the hypothesis is P if and only if Q, and this implies that P implies Q, and I want to show this as a tautology. I'm going to take the outer implication here and rewrite that as negation of hypothesis, disjunction, conclusion, like so. But now I have the biconditional that can be rewritten as P implies Q, conjunction Q implies P. I now have negation sitting on top of a conjunction, so by De Morgan's laws I can distribute at the cost of changing the conjunction to disjunction. So I now have a series of disjunctions here. But notably I have P implies Q and P implies Q. Since the disjunction is commutative and associative, I can regroup this so that the P implies Q bits are actually next to each other. But this is going to be negation of P implies Q, disjunction P implies Q. This actually is the law of excluded middle, which is always true. And true is the absorbing element for disjunction, so the other statement gets absorbed into a true statement. So this statement is true. This is indeed a valid argument. With the ability to argue from an equivalence to an implication, the rules of inference can now be applied directly to equivalences or a blend of equivalences and implications. Moreover, several of the properties previously established for the connectives can be rephrased as arguments. By means of these arguments, one can then show that each of the 5 connectives preserve equivalences in a satisfying way. Let's start by showing that modus ponens can be used with an equivalence. So in this argument, my premise is P. My second premise is P is equivalent to Q, therefore Q must be true. So how would this go? How would a formal proof like this go? Well, my first step will be to use the first premise, P. My second step will be using the second premise, that is P is equivalent to Q, like so. Now, as demonstrated a moment ago, P is equivalent to Q implies that P implies Q, which I'll call the simplification of the biconditional using step 2. But now I have that P is true, and P implies Q is true. So by modus ponens, using steps 1 and 3, I now have that Q is true. So this basically shows that one can use modus ponens not just from an implication, but from a biconditional just the same way. I can also do this with modus tollens, basically the same way. The proof would go very similar. My first premise, my first step here will be negation P. My second premise, my second step will be P if and only if Q. My next step will be to simplify this, but this time I'm going to simplify it down to Q implies P instead, simplifying the biconditional the other direction. Now using modus tollens, negation P, Q implies P with steps 1 and 3, gives me that negation Q must be true. Thus one can use a modus tollens with an equivalence just as much. From the modus ponens argument above, one can now prove equivalences by means of 2 dual implications. For some terminology, for sentences P and Q, the converse of the implication P implies Q is the implication Q implies P. Basically, the converse of an implication reverses the roles of hypothesis and conclusion. Using the restatement of the biconditional, one can now prove an equivalence via the implication and its converse. The argument goes like this. P implies Q, Q implies P, therefore P is equivalent to Q. So how does one show that this particular argument is valid? Well, here's a proof of this argument. The first step I have is going to be the first premise, P implies Q. The second step will be the second premise, Q implies P. Using adjunction with the steps 1 and 2, I now get that P implies Q conjunction Q implies P happens to be true. This is where I'm going to pull one of the properties of the connective, something I've proven previous and now use as a step here, which is that P implies Q conjunction Q implies P is equivalent to P if and only if Q. I now use modus ponens with steps 3 and 4, which gives me that P if and only if Q happens to be true, concluding my proof. The hypothetical syllogism was discussed previously, which itself is the transitive property for the implication. Likewise, the biconditional is also transitive in the same fashion. What this means is that if you have P implies Q and Q implies R, that tells me that P implies R. In a similar way, you have if P is equivalent to Q, Q is equivalent to R, that tells me that P is equivalent to R. However, the two can be mixed together, giving me two other forms of the hypothetical syllogism. Here's another form of the hypothetical syllogism. The first premise is P is equivalent to Q, Q implies R, therefore P implies R. So, how would a proof of this happen to work? Well, it goes as follows. The first step will be the first premise, P is equivalent to Q. I can simplify that down to P implies Q, changing the biconditional into an implication. I introduce the second premise, P implies R. I now have P implies Q, Q implies R, by the hypothetical syllogism with 2 and 3. That now tells me that P implies R, completing the proof. I can also do this the other way around. What if I have P implies Q, Q is equivalent to R, that is going to tell me that P implies R also. The proof is very similar. I'm going to start off with the second premise, Q is equivalent to R. I can simplify that to Q implies R, introduce the first premise, P implies Q. I now have P implies Q, Q implies R. By hypothetical syllogism with steps 2 and 3, I now have that P implies R, completing this proof as well. Next, consider rephrasing the properties of the connectives as arguments. For instance, consider the litotes property of negation. I want to state it as an argument, and here's one way I can state it. P, therefore negation P. I want to show that this particular argument is valid. Well, here's a proof of this argument. The first step will be the first premise, which is P. I'm now going to pull the litotes property, which we've already shown is true. That is, P is equivalent to negation P. Using modus ponens with step 1 and step 2, I now conclude that negation P must be true, completing the proof. I can also do this the other way around. If I start with negation P, I can then conclude that P happens to be true, and the proof is basically a mirror image. The first step is the first premise, negation P. I pull in the litotes properties that negation P is equivalent to P, and then I conclude by modus ponens that P happens to be true. Thus, I can use one side of the litotes property provided that the other one already exists. The litotes law is not the only property that can be rephrased as an argument. Using similar proof, one can prove the validity of each of the following arguments. For example, you have the associative law for conjunction in both directions, the associative law for disjunction in both directions, the associative law for the biconditional in both directions. You also have the commutative laws for the conjunction, disjunction, and the biconditional. You also have the distributive law for the disjunction over conjunction in both directions, and the conjunction over the disjunction in both directions. You also have De Morgan's laws. You have negation on top of conjunction in both directions, as well as negation on top of disjunction in both directions. All of these arguments have basically the same proof. Lastly, recall that the negation, conjunction, and disjunction each preserve equivalences. That is, acting on both sides of an equivalence results in an equivalence. For example, if you have P is equivalent to Q, then that tells me that negation P is equivalent to negation Q. If you have P is equivalent to Q, then that tells me that P conjunction with R is equivalent to Q conjunction with R. Likewise, if P is equivalent to Q, that tells me that P disjunction with R is equivalent to Q disjunction with R. However, the latter two can be generalized even further. Given two equivalences, the conjunction and disjunction can be used to create a new equivalence. First, let's show that the conjunction preserves equivalences in the following way. My first premise is going to be P is equivalent to Q. My second premise is going to be R is equivalent to S. I want to conclude that P conjunction with R is equivalent to Q conjunction with S. That is, if I conjunction the left-hand sides and conjunction the right-hand sides, the results should both be equivalent. So, how do I demonstrate that this is a valid argument? Well, here's the proof that I'm going to use. I'm going to start with the first premise, which is P is equivalent to Q. Now we've already demonstrated that if I conjunction both sides of this equivalence with some fixed statement, say for example R, I get another equivalence. That is, P conjunction with R is equivalent to Q conjunction with R. So notice that R is on the right-hand side of both of the conjunctions, and it's the same on both sides like this. So how do I get S into this? Well, what I'm going to do is I'm going to do a little bit of finagling. I'm going to do a little bit of commutativity. Now remember, I have the commutative law for conjunction, so I can rearrange this so that the R is on the other side. So Q conjunction with R is equivalent to R conjunction with Q. Also, the biconditional, that is the equivalence, is transitive. So P conjunction with R will now be equivalent to R conjunction with Q, giving me this line right here. Now, I do this because I'm now going to introduce the second premise, R is equivalent to S. And what I'm going to do now is hit both sides of this with conjunction with Q. So now what I'm going to do is, with transitivity, P conjunction with R is now equivalent to S conjunction with Q, giving me this statement right here, which is almost the conclusion I want. I just need to commute them back. So I take S conjunction with Q and reverse it. So S conjunction with Q is equivalent to Q conjunction with S. By transitivity, P conjunction with R will now be equivalent to Q conjunction with S, giving me the conclusion that I wished. Now, I did this for conjunction. How would I do this for disjunction? Well, turns out the proof is nearly identical. Just swap out every time I said with conjunction with disjunction, and that gives you a proof for the disjunction case. Now the implication and biconditional can be shown to preserve equivalences in the same way. For example, if I have P is equivalent to Q and R is equivalent to S, I can conclude that P implies R is equivalent to Q implies S. How I'm going to do this is to just bootstrap up the disjunction property I just showed. So I'm going to start with the first premise, P is equivalent to Q. Now we already know that negation preserves equivalences, so negation P is equivalent to negation Q. I now introduce the second premise, that is R is equivalent to S. I now use the disjunction property that we just showed. Disjunction the left-hand sides, disjunction the right-hand sides, that gives me this. Negation P, disjunction with R, is equivalent to negation Q, disjunction with S. I'm almost done. All I need to do now is reformulate these into implications. So let's use that. Remember that P implies R can be reformulated, that is equivalent to negation P disjunction with R. By transitivity, that gives me P implies R is equivalent to negation Q disjunction with S. Do this one more time. Negation Q disjunction with S is equivalent to Q implies S. So I now, by transitivity, have that P implies R is equivalent to Q implies S, completing the proof. Bootstrapping up one more time, I can actually get the biconditional. So let's take P is equivalent to Q, R is equivalent to S. I want to conclude that P if and only if R is equivalent to Q if and only if S. I'm going to go ahead and put the premises on the board. P is equivalent to Q and R is equivalent to S. We've already shown that the implication preserves equivalence. So P implies R is equivalent to Q implies S. That's the thing we just showed. But by the same token, I can do it with the converse as well. R implies P should be equivalent to S implies Q by the same token. Now what we're going to do is I'm going to conjunction the left-hand sides and conjunction the right-hand sides to give me this statement using the conjunction preservation property. I'm almost done. All I need to do is rearrange these into biconditionals, and I'm done and sorted. So remember that P if and only if R is equivalent to P implies R conjunction R implies P. So by the transitivity property, I have P if and only if R is equivalent to Q implies S conjunction with S implies Q. Do this one more time. Q implies S conjunction with S implies Q is equivalent to Q if and only if S. So by transitivity, I have P if and only if R is equivalent to Q if and only if S, completing the proof. And that's where we'll stop for today. Next time we'll discuss argument reformulation and proof strategy. Below is a list of references for today's video. We have Learning to Reason, an Introduction to Logic, Sets, and Relations by Rogers. We also have a First Course in Mathematical Logic by Suppes and Hill. If you like today's video, go ahead and hit the like button below. If you have a comment or a question, go ahead and leave that below as well, and we will respond to you as soon as we can. Thank you for your time, and we'll see you next time. See you then.